What's going on, everybody? Johnny Bandon here, the networking guru. In today's video, we're going to be going over domain 1.4 of our Security Plus full self-paced course. This video is going to be going over the different encryption algorithms, so symmetric versus asymmetric encryption algorithms. I call this domain 1.4.1. I like to section off my videos. And before we get started, make sure you like, subscribe, share with your friends, hit that bell for notifications. Now let's jump into our lecture. So I'm going to zoom my face out of the way here. And again, we're going over domain 1.4.1. So the 1.4.1 is something I made up. It's just how I section off domain 1.4 of the actual Security Plus exam objectives, because I don't want to make a 3-hour video just on domain 1.4. So this is explain the importance of using appropriate cryptographic solutions, encryption algorithms. So you can see these are the full exam objectives here for domain 1.4. You have encryption and a lot of things about encryption, different levels. We have PKI components, then also cryptographic tools. Today, we're just going to be going over the algorithms and also some key exchange, and of course the algorithms asymmetric, symmetric. And then I believe in this video we touch on key length. We'll have to see towards the end. Okay, so first, let's start off with what is encryption. So encryption is a process of converting information or data into a code, especially to prevent unauthorized access. So let's break that down. What we're saying here is that data coming across the wire, if we were to do a packet capture on it, and this is just data, think of raw data back in the 80s. There was no HTTPS or any encryption, maybe just FTP transfer, TFTP transfer. If we were to splice that cable open from my computer to my switch to my server, I could see that. I could see those bits that get turned into data, human readable data, and I could see it. It would be in what we call plain text. Encryption is the process of converting that plain text into something called ciphertext, where it becomes unreadable, where you can't have access to that data because it's encrypted. And unless you have the key to decrypt it, to decode that encryption algorithm that we put on that data, well, you're not going to be able to read it. So in short, encryption turns our plain text readable data into non-readable, non-accessible ciphertext data. So encryption uses an algorithm and a key, two main components of encryption, an encryption algorithm and a key, to transform readable data into a non-readable format, plain text into ciphertext. The key is a piece of information or sequence of bits used by the algorithm to perform that encryption. So you can't have one without the other. I can create an encryption algorithm, but to encrypt and decrypt, I need a key to lock and unlock, to activate and deactivate that encryption algorithm. So encryption, algorithm, and a key that turns plain text into ciphertext, readable into non-readable. And we do this on data in transit, data at rest. We can also use it data in use or in processing, which we're not going to touch on. But if my data is coming from my computer to a web server, we can encrypt that data in transit end to end. If I have a computer sitting here with 1,000 or with a terabyte of disk space, I can do full disk encryption to encrypt that data at rest. Now, with that basics out of the way, why do we use it? So let's go over this as well. Why do we use encryption? So confidentiality. To ensure that sensitive information like personal data, financial information, maybe we're getting in compliance with PCI, or confidential communication remains inaccessible to unauthorized individuals. So back to like the CIA triad, confidentiality. How do we gain confidentiality on our data? One way is in encryption. Authentication. So in asymmetric encryption, the use of private keys for decryption proves the identity of the user by using its public key. We'll get into that. Serving as a form of authentication, and this is specifically used with our digital signatures. Non-repudiation. So digital signatures, a form of asymmetric encryption, and what we're really talking about here is digital signatures use asymmetric encryption algorithms to be created, ensure that the sender cannot deny the authenticity of their sent message. So encryption algorithms, specifically asymmetric, can give us something called non-repudiation, where we can verify that it is that original sender that sent our message. We'll get into that later. Compliance. And then, of course, we need encryption for compliance, whether that be government, finance, health, encryption is needed to protect our sensitive data, and we need certain levels of encryption depending on our industry. So HIPAA, PCI, DoD NIST standards may have specific encryption standards that we need to apply to be in compliance, to put our data on that network, or to be in that sector, to be in that industry. What I mean by that is, if we use AES encryption in the DoD, there may be some standard that says you need to use 256 when accessing like secret levels of data or networks. Now, the first encryption algorithm we're going to talk about, or encryption type, is symmetric encryption. In symmetric encryption, the same key is used for both encryption and decryption. Remember, how do we achieve encryption? We have an algorithm, and then we have a key that activates and deactivates that algorithm. Or more accurately, encrypts and will decrypt. That's the key here in our algorithm. 2 pieces for encryption. So in symmetric encryption, we just have a single key that will encrypt and decrypt, meaning the sender and receiver must both have access to that secret key, and then they must safeguard that key. So if I'm Bob, well, my name's Johnny. Let's just use my real name. I'm Johnny, and I need to send Alice a secure message, and I'm using symmetric encryption. I will create a shared key or a secret key, encrypt my data, send that data to Alice, and then I have to send that key to Alice so that she can decrypt my encrypted message. That's symmetric encryption. So some example algorithms are AES, the Advanced Encryption Standard, very common one we're going to talk about. Then we have DES or DES and triple DES, which is antiquated, it's no longer secure, but we bring it up. Use case. Symmetric encryption is often used for encrypting large amounts of data, such as database information or files on a disk. Symmetric encryption is also used in data in transit, like our TLS cipher suites will have stream ciphers, symmetric encryptions that we use. But for like testing purposes, when we need to bulk encrypt and we need efficient use of our compute to encrypt, symmetric encryption. Symmetric encryption uses less computation to encrypt compared to asymmetric encryption. So you may get a question maybe in your studies that's like, we need to encrypt large amounts of data, and what encryption algorithm would be best, symmetric or asymmetric? It's going to be symmetric. Now we're going to go over the process of symmetric encryption. So here we have Amanda's laptop, and she is going to send a message here that says, hello, Steven. It's in plain text. She wants to encrypt it. So we use a symmetric encryption algorithm. Amanda is going to create a secret key for that algorithm. So maybe she's using AES. She's going to use that key to encrypt her message, converting that message into ciphertext. She'll send that to the receiver, Steven. Steven's going to get that encrypted message and say, well, I need a way to decrypt this. So he's going to use Amanda's secret key to decrypt it, and now he can see that message. It's now readable. So easy process, I feel, to understand. But what is an issue we have here? Or what may be some vulnerability of symmetric encryption? This process here, of Amanda's secret key, how did that happen? Did she walk over and hand Steven a USB that said, here's my secret key? And therein lies the problem. It's the transfer of that secret key. How do we keep it secure? How do we send that secret key to Steven, who may be sitting in Washington, and Amanda's in Arizona? Remember, this is over the network. We're not actually handing off keys. We're not going to Lowe's and getting a key made. How do we handle that? Well, when we want to use a shared secret key to use a symmetric encryption algorithm to encrypt our data in bulk and in transit, guess what? We use asymmetric encryption, and I'm going to go through this in about 10 minutes. You'll see what I'm about to say, to generate a shared secret key between sender and receiver. Keep that thought. But just for the general process of how symmetric encryption works, that's it. If I want to encrypt something using symmetric encryption, I create a secret key, I encrypt, send it to the receiver. That receiver needs that same secret key, okay? Another issue with this is it doesn't scale very well, right? Because now imagine the return. Steven needs to send encrypted traffic back. He might use his own key, which means he has to send that key. But imagine if he talks to Bob, or I introduce 10 more people, and now he has to send that key to 10 people. It can get very complex. A lot of those issues are resolved, or they are resolved, with asymmetric encryption. So what is asymmetric encryption? Also known as a public key cryptography, it involves 2 keys, a key pair, what we call a public key and a private key. Just a little, extra information though. The designation of public or private key really doesn't matter. What matters is that when we use asymmetric encryption, those two keys are mathematically related no matter what. I could call it my favorite key and my least favorite key. It doesn't matter. What matters is that they're mathematically related. Now, we call them a public and private key because how we use them, that terminology makes the most sense, okay? And what do we mean by that is whatever the public key does, the private key undoes, and vice versa. Whatever the private key does, the public key undoes. So to break that down even further and be more accurate, if the public key encrypts, the only thing that can decrypt that information is the private key. If the private key encrypts, its public key pair is the only thing that can decrypt. So if this user here creates key pairs and he encrypts with his public key, only his private key can decrypt. So now, we create two keys with asymmetric encryption. We designate one as public, we designate one as private. And when I say when we're on the computer and we generate like SSH keys, which uses RSA, which is an asymmetric encryption, it creates a public and private key, right there on the spot. So the public key, this can be shared openly. So in typical asymmetric encryption, the public key is going to be open to everybody, meaning that maybe I'm encrypting emails and I put that on our global address list or some registry within our enterprise that says, here's my public key. It's open. It's public. It doesn't have to be safeguarded. And in typical asymmetric encryption, like, transmissions, that is the key that encrypts. The private key is very similar to that symmetric key in the fact that we have to safeguard it. The private key will be kept secret by the owner and is used to decrypt that data. So some examples, RSA, ECC, Diffie-Hellman are all asymmetric encryption algorithms. RSA famously most used with SSH. If you're a network cybersecurity IT administrator, I'm sure you've dealt with SSH before. That's asymmetric encryption. So use case. Asymmetric encryption is commonly used for secure key exchange, digital signatures, and encrypting small pieces of data like passwords. Look at this here, secure key exchange. We're going to come back to that. Because remember I said symmetric encryption is what we use for that bulk data encryption, and that's what we use from like doing TLS, client to web server, and symmetric key to actually encrypt. We're going to come back to that because we use because what was the problem with symmetric encryption is the exchange of that key is not secure. So we're about to do it. Asymmetric encryption is used for secure key exchange to create a secret key to use symmetric encryption. I'm getting a little tongue-tied, so we're going to move on. But use case, yes. Asymmetric encryption is commonly used for secure key exchange, digital signatures, and encrypting small pieces of data like passwords. So here's how it works. We have our sender and we have our receiver. We have Amanda here. She wants to send a message to Steven. It's plain text. So we're using asymmetric encryption now to encrypt this message. So both the sender and receiver are going to create key pairs, a public key and a private key. So we have Steven's public key and Amanda's public key, and Amanda's private key and Steven's private key. The private keys stay local. The public keys are there for us to use. So when the sender here wants to talk to our receiver, Steven, using asymmetric encryption algorithm, Amanda's talking to Steven here, what key are we going to use to encrypt? We're going to use Steven's public key. That's right. Because what is the only thing that can decrypt that? Steven's private key. So you may say, well, if we're just using everyone's public key to encrypt, how is that safe? Because remember, if the public key encrypts, the only thing that can decrypt is the private key. The public key can't encrypt and then decrypt. That's not how it works. If the public key encrypts, the private key decrypts. And if we're using Steven's public key, our receiver's public key, to encrypt, his private key is the only thing that can decrypt that message. And that is stored locally. That is safeguarded. So the sender, Amanda, is going to take Steven's public key and encrypt. It's going to get sent to Steven. Steven's going to say, okay, I see an encrypted message here. I have my private key. I'm going to decrypt it. And if it works, guess what? That my public key was used to encrypt this. So Steven's then going to take his private key to decrypt. And that's how simple it is. That's asymmetric encryption. You take the receiver's public key to encrypt your message as the sender, send it to the receiver, then the receiver will use his or her own private key to decrypt. Now, how does this create secure key exchange? So shared secret key exchange. So imagine like our TLS sessions or HTTPS sessions with a public web server. In a short version, we take that public web server's public key to do the initial communication encrypted session. Then we use that asymmetric encryption to create a shared secret key using a formula like Diffie-Hellman key exchange. And then our session there has a unique shared secret key just between client and sender. So let's break this down. Look at this image here. So how do we use asymmetric encryption to get a shared secret key to then do symmetric encryption? Well, if we use Diffie-Hellman, here's how it's done. So Alice and Bob, they want to create a shared secret key between each other so that they can use symmetric encryption to send their traffic. They're sending gigabytes of data to each other. So they're going to do an asymmetric encryption algorithm, and they're going to initiate their session. They're talking using asymmetric encryption. So Alice creates her key pairs, private and public. Bob creates his key pairs, private and public. What's going to happen is Alice and Bob are going to share with each other their public keys. So Alice is going to take her private key and Bob's public key, do some math that we're not going to discuss here, but you see it's just driven. They're going to add, right? They have a formula. But she's going to take her private key and Bob's public key, do the Diffie-Hellman algorithm, and produce a new key. Bob is going to do the same thing. Bob is going to take his private key and Alice's his private key and Alice's public key, do some Diffie-Hellman algorithm math here, and create a new key. These two new keys are now mathematically related, and now they cannot be recreated at all, and that's your new shared secret key. So what Diffie-Hellman key exchange, an asymmetric encryption algorithm, allows two parties to generate a shared secret over an unsecured communication channel. That's how asymmetric encryption allows us to create a shared secret key to then do symmetric encryption. That's a mouthful, but that's how it works. Now, I'm not going to get into how it does it, right? There's like prime numbers, a whole algorithm behind it, but that's how we use asymmetric to create a symmetric key that is private. And that gets over our limitation of pure symmetric encryption of the secure transfer of that key. So this is a big part of encryption, our overall ecosystem. When we're doing like public key infrastructure, the whole ecosystem comes together using asymmetric to generate a symmetric key. And we have these key exchange algorithms like Diffie-Hellman and elliptic curve cryptography that allow us to do that. So Diffie-Hellman, like if you see it on a question that says, what's its purpose? It's for shared secret key exchange. ECC does the same thing. So ECC is a form of public key cryptography or asymmetric encryption based on algebraic structure of elliptic curves over finite fields. I can't and I won't dive into how ECC specifically works because this is a Sec Plus foundational exam, but it accomplishes the same thing as Diffie-Hellman, where we use this algorithm to do shared secret key exchange. Okay? So, in both Diffie-Hellman and ECC, the shared secret key derived from these exchanges is typically used to encrypt further communication using symmetric encryption. This approach combines the security of asymmetric encryption for key exchange with the efficiency of symmetric encryption for data transfer. And when you look at like TLS cipher suites, and it'll tell you like we're using RSA with DHECSDA and then Salsa 20, which we'll get into in the later videos. That's what we mean by cipher suite. We're using this asymmetric encryption to establish secure key exchange, and then we get that key, and now we're using this symmetric encryption to actually encrypt our data in transit. Okay, now just diving into some of the actual algorithms. So we have triple DES. So this is a symmetric encryption algorithm, how it works. It's based off DES, but triple DES applies the DES algorithm 3 times. Triple DES uses either 2 or 3 unique keys, effectively increasing the key length to 112 or 168 bits. One thing I forgot to talk about. Encryption keys will have a bit key length. The higher the bit key length, the more secure that encryption is. So with AES, or triple DES, which is stronger? 112-bit or 168-bit key using that encryption algorithm? It's always the higher number. RC4, this is a stream cipher that generates a pseudo-random stream of bits, a key stream, For encryption, the key stream is combined with the plaintext using a bitwise XOR operation, and it supports keys ranging from 40 to 2048 bits. Important for the exam. RC4 was used in older protocols, but it's now vulnerable. So that's what you need to know for RC4. All this, how it works, there's plenty of training to dive deep into how these encryption algorithms work, but what you need to know is that RC4 is a symmetric encryption algorithm that's now vulnerable. It can be exploited. Okay, one that I missed here on the slides is AES, the Advanced Encryption Standard. That comes in 128-bit, 192, and 256-bit key lengths, and that's a symmetric encryption algorithm as well. That's like the standard AES. But moving on to what we have here on the slide, an asymmetric encryption algorithm, RSA. So RSA algorithm is based on the mathematical difficulty of factoring the product of two large prime numbers. Whew. Listen, RSA is used for asymmetric encryption. It's used for SSH, it's used for SSL and TLS, and we don't have to dive into how the key is generated. If you see RSA on a question, it is an asymmetric encryption algorithm. Okay? Alrighty, now let's do our quiz. So I'm on my custom learning management system on our academy here, and I'm going to go take our domain quiz. If you want to purchase this, check the link in the description or go to trepatech.com. So we're doing domain 1.4.1's quiz, which is going over the encryption algorithms. So question 1. Which of the following is a common use of asymmetric encryption? Let's see. Encrypting data stored on a hard drive. That's going to be symmetric encryption. That's that bulk. Compressing data to send over email. Now, we do use asymmetric encryption for like digital signatures, which can be attached to emails. That's common, but I don't think it's C. Speeding up the data transfer. Encryption never speeds data transfer up. But what it does do is it will encrypt data in transit, like in secure web communication. Remember, like TLS, we first had to do asymmetric encryption, and then do secure key exchange, and then that leads us to our stream side for our symmetric encryption. So we're going to go with B here. Pause the video if you'd like to read the explanation. Question 2. What is symmetric encryption? So A automatically is a correct answer. Encryption where the same key is used both for encryption and decryption. So I'm going to do that. And A is our correct answer. Pause the video if you'd like to read the explanation. Question 3. What is encryption? So it's not a process of compressing data. It is a method of securing communication by converting information to an unreadable format. More simply put, plain text into ciphertext. It's not a technique for speeding up computer performance, and it's not in itself a protocol for transferring data. So we're going to go with B. A method of securing communication by converting information into an unreadable format. Pause the video if you'd like to read the explanation. Question 4. What is asymmetric encryption? So we have A method using different keys for encryption and decryption, where one is public and the other is private. That is accurate. We'll read the other options though. An outdated encryption method, no. A faster method, nope. Symmetric is, I wouldn't say it's faster, just uses less compute resources, less CPU RAM. Encryption used for creating digital signatures only. It does create digital signatures. That's not the only thing it does. We're going to go with A here. A method using different keys for encryption and decryption, where one is public and the other is private. Pause the video if you'd like to read the explanation. All right, and there we go. We got 100%. I want to thank everyone for viewing. Make sure you like, subscribe, and if you're enjoying this, share it with your friends, and I'll see you in the next video.